did tell my 2810 class that we didn't have class today unless they wanted lab. I would be there for lab. No, it's not really a lecture day. But you guys have new material this week. We're going to be talking about number theory, and as you can see here, we've got things like testing for primality, Euclid's algorithm. This just happens to be it's an iterative one, but it's an iterative one that uses modulo versus an iterative one that uses that would use subtraction. I like the subtraction personally, but that's just me. And then down at the bottom here, it's not labeled, but this big boy down at the bottom is actually what's called the division algorithm. And we're going to introduce all three of those today and talk about how they're used. But first, a message from your sponsor. We've got a little bit of review, and then we'll get into things. We'll first talk about the idea of divisibility. We have what's called a divisibility operator. It returns a true or false whether something divides something else. And it's very closely tied to the idea of modular arithmetic. We'll then talk about representing information inside the computer. In particular, we're going to be looking at only positive numbers. We can talk about negative numbers if you want. We'll talk about primality, least common multiple, and greatest common divisor. Probably the most of our time will be spent on the greatest common divisor. So let's go ahead and get to it. What's an algorithm? It's a song you give about a 3 out of 10 or 6 out of 10. Got a good beat, but doesn't have a good melody. No, as you know, it's actually a finite sequence of steps. In other words, finite, we're eventually going to reach a conclusion of some sort, some finite number of steps or instructions that allow us to solve a problem or perform a computation. Some important characteristics of it are things like it has input and output. So our algorithm does not work in a vacuum. It actually takes some sort of input, like a specific pair of shoes or a specific pattern of streets and their traffic flow, whether there's one-way streets or other stuff like that. So it would have an input of some sort, data, a start point, a stop point for a navigational program, a specific pair of shoes with the shoelaces associated with them for tying shoes, and then it'll have an output. It will have some things that are done and some end result that comes out of the other end. It has definiteness in that each step is precise. Telling you to turn right, having been in the military and watched people march, I know that there are some people that don't understand the word right or left, but it's still, those are two still very definite terms in most languages. Correctness, we want to make sure that it produces the output that we're looking for. As we talked about last time, there are some algorithms that we use that are designed specifically for approximation. So we don't anticipate that they're going to produce the perfect answer, but we do expect them to produce the same answer all the time. And we would consider that correct, assuming that it's one that we can predict from the inputs. So therefore, it would be the one that we would expect it to be. And then we want finiteness. Not just a finite number of steps, but we also want the ability to determine our algorithm is going to stop at some point or another. And then effective, this would be the one that would be a measure of performance, which is one of the main things that we talked about last time. How well does it perform? How well does it solve the problem? How much time does it take? And does it take you, in order to get you to Denver, does it take you to Acapulco for a week? Well, if it's paying for airfare, sure, that's fine, but otherwise it's not necessarily as effective as some other. We also looked at different types of algorithms. I believe I forgot to mention our middle one here, so we'll get to it in the review and we'll press on from there. What's the greedy algorithm?
That's the one that makes the best move for each step, right?
It decides what looks best right now. It's like 3 or 4-year-old in the candy store. They walk in, they grab the first thing that looks good to them. They don't necessarily wander around the store figuring out what their options would be. They grab the first thing. This would be that kind of algorithm. Sometimes we do that because we can't predict what's going on in the future. But it's just a general method for solving some problems. We try and reach our goal by choosing some best local choice. What information do I have at this point? You could view this as trying to play a game of chess by playing the piece or the move that you think is going to be the best at that point, and not playing 2 or 3 moves ahead and trying to trap the other person or avoid traps or things like that. So we try to get to the top of a mountain, for example, by always walking up. That would be a problem from here because once you reach 89, I was thinking we were at the Davis campus. Actually, that wouldn't be too much of a problem here on the Weber State campus if we wanted to get to the top of the closest mountain. If we wanted to get to the tallest mountain in the 48 states, it would be a problem. We would never get there because we can't walk up the entire time. We're going to have to walk up and down and up and down and up and down to get to, I think the tallest one in the 48, in the lower 48 is in Colorado. I know it's got more 14ers than anybody else. I don't know. But the idea here is that by choosing that using the greedy algorithm to select things, we don't always get the best solution. You can't play the best game of chess by only choosing, oh, I want to move this piece because it looks like it's going to get me the closest to the other end of the board. But you have some measure that determines what's a good move and what's a bad move, or what your choice, some way of ranking the choices. It's like having the backpack with, that'll hold 20 pounds. If you see a 17-pound bar of gold, don't put the 17-pound in until you find out what the other bars of gold look like. Brute force is the one I didn't mention last time. We also call this enumeration. It's listing all possible values. If you were to do this for chess, how long would you be here? A while. A really long time. It's like 10 to the, if I remember it, it's 10 to the 10,000 or 10 to the 10,000 power, roughly, for the possible number of chess games that can be played. And of course, that makes the assumption that you're not moving pieces back and forth just continuously. Oh, I'm going to move my knight out. Oh, wait, let me move my knight back. So there's brute force is kind of a way of listing all those things, and we usually do this when we don't know what it is that we're going. Oh, here we go. It's not 10,000. Well, heck, this is a small number, and actually, this represents only the most common chess games. Typically about 10 to the 120th. Yeah, you'll be able to hear a long time. If you go to this link, what you'll get is, let me bring it over here. How many different ways can a chess game unfold? 10 to the 120th is actually not all of them. It's more the 40 move common games. So you've got 40 possible games there. So 10 to the 15th total hairs on human heads, 10 to the 23rd grains of sand on Earth, 10 to the 81st atoms in the universe. So I don't know where they got those numbers, so obviously we have to take this with a grain of sand or salt or whatever. But yeah, 10 to the 81st atoms in the universe, that seems like an awfully small number, but you never know. So there's a link in the slide presentation to that particular one. A brute force enumeration, therefore, would take more memory than we could possibly represent, and we wouldn't be able to find it. But a lot of optimization problems end up being enumeration. And as we'll see in next week's class, where we start talking about counting and using permutations and combinations, enumeration can grow very quickly. It's a factorial kind of problem. What is here? The final one is divide and conquer. We talked a little bit about this. In this case, I have to have a problem where each portion of the problem ends up being essentially the same thing. So I'm breaking it into smaller and smaller pieces and finding some way to combine the results. This ends up being a recurrence kind of relation when it comes to solving it. And in those kinds of cases, we would use what's called the master method in order to figure out what's going on. And what that does is take a look at what the recurrence formula looks like and tells us, oh, you've got an exponential problem, you have an n log n problem, you have another kind of problem. So it gives us a form for the formula of how long it would take to solve the problem using divide and conquer. So why do we care? It tells us about what we can do with computers, how long it's going to take, about how we can solve problems. There are some problems, this is where the 10 to the 10,000th for all possible games, and 10 to the 120th, 10 to 120 for typical games. But some problems are intractable. Too much room, too much memory or time. It just takes too much to solve it. We can't solve it because it's just too big in one dimension or another, either time or space, sometimes both. It doesn't do us any good to solve problems like, if you could solve world peace with a computer, but it was going to take, 1 billion years, just look at what happened over the weekend. We've got another war going on now, and we're likely to destroy ourselves before we have the computer be able to tell us what to do. Unless, I read a piece over the weekend. Have any of you ever heard of Colossus, the Forgan Project? It's a movie that came out around 1970. 1970-ish. It was the first movie talking about AI taking over the world. So, kind of a neat one if you avoid looking at the blinky lights and saying, oh, those are great special effects. The story itself is actually pretty good. We also talk about the idea that there are some problems that have no solution. We will look at this in greater detail, not a whole lot more, but greater detail in Module 13. But it's one of the reasons why we oftentimes will come up with estimates on things, is that we can't really solve the problem, so we'll try and get close, and close is good enough. So if you're a Dirty Harry fan, then you understand that what we're talking about here is we have to know what we can and can't do with a computer. What are our limitations, and how can we press forward from that? When it comes to problems, we need to know things like, can we solve it? I did have one person that was employed somewhere, and they said, yeah, we never really need any computational theory. We don't care whether or not you can solve the problem or how good the algorithm is. You might, depending on the type of problem. The question is, will you still be alive when the answer comes out? If we're not, then maybe we might want to change the way that we actually do it. But we talked about growth of functions, both in time and space. And we looked at different notations, asymptotic notation that talk about this. Big O notation is an upper bound. It's a worst case. What's the worst that our program can perform, either in time or space? So we have to have some measure of the algorithm and the problem that we have. We also have a best case. We might never be able to, my worst case might be a factorial problem, and my best case might be a linear problem. That would be, the question at that point would then become, well, what's the most common case? because I might start it off and say, well, if I start getting over like some multiple of a linear value or like an n squared value, at that point, I might decide, well, I can't wait for the factorial solution, so I'm not going to try and solve that specific problem. But there might be general problems, or the most probable problem might be one that would have a solution that is in a better time. So it might be closer to our omega, big omega kind of time there, where we're looking at, what's my best case? If my average case approaches my best case versus my worst case, then I might accept it. Anybody in here know what the worst case time for quicksort is? Yeah, when you take 2420, one of the things that you'll look at is sorting algorithms, because they're one of the key ways that it gives us a good way to talk about the order of something. But it's not just the big O, we also have to consider the big omega and the average case. Well, in the average case, quicksort is an n log n algorithm. It's pretty much the same as, it's got a smaller multiplier, if I remember, a smaller multiplier than merge sort. But there are some degenerate cases for it that are n squared. So the question is, how often do those degenerate cases come up? And we try and avoid those. Can I look at the data ahead of time and determine that sort of thing? We might also want a type bound, and that would mean that no matter what, best case, worst case, we're always going to perform some way. That would be our big theta notation. And that just basically says that no matter what we do, we're always going to end up with a function that performs in a specific way. We can define it as performing on the order of something. If there is no big theta, then we have a worst case, which would be our big O, and then we look at an average case. So that's the kind of the way that we approach solutions to problems. If we can figure out what the form of the solution is, then it gives us the ability to determine, do I want to solve this or not, or is this a good way to solve this particular problem? So let's get into some number theory now. Divisibility and modular arithmetic. If I have two integers, a and b, and a not equal to 0, we can say that if b is divisible by a, or b divided by a is an integer, in other words, there is no remainder, then we say a divides b. So in this case, a would be our smaller value, and we would say that a is not 0. Why would we say a is not equal to 0? Because a divided by b, or b divided by a would be infinite. We wouldn't have an answer for it. So in that case, it's not really defined, but we can talk about some number dividing another number. And this is another instance where we use the vertical line and we say a divides b. And you might say, why do we do that? Well, it's because we're kind of related to mathematicians. They're kind of our distant cousins. We work with them sometimes. We do stuff that they do, but we're not often involved in everything that they do, though we do like some of the stuff they do in the discrete realm. And this is definitely discrete because we're talking about integers. So the idea here is that if some number b divided by a is evenly divisible, then we say a divides b. We use that for factoring, we use it for all kinds of other stuff. And that's really kind of what we have. We also say b is divisible by a, or b is a multiple of a, would be other ways of actually saying this. But if you're talking to a mathematician, they're going to want to secure the word divide. So a divides b. Tell me that. Give me the little vertical bar here. That's one of the things that we don't normally use. We can also say that a is a divisor or a factor. So that means a times c is going to equal b. So a is a factor of that particular value that it divides. As an example, 13 divides 39, and 11, well, 11 doesn't quite divide 43 because the result I get there is something just a tiny bit less than 4. So 11 does not divide, and we just draw the line through. The symbol that I have on the keyboard is not quite as good. The little line going through the operator is not very big. But 13 divides 39, 11 does not divide 43. And we can say that because 39 divided by 13 is 3, 43 divided by 11 is not quite 4. So we've got 1/11th. 1/11th would be what, 9.999999999. So it would be 3.111, something like that. We do get some interesting results from this, interesting from a mathematical perspective. If A divides B, in other words, A is a factor of B and A is a factor of C, then A is a factor of or divides B plus C. So if that means that this is the same thing as saying that it's the same thing as saying that B divided by A is equal to I, and C divided by A is equal to J, then B plus C divided by A will equal B divided by A plus C divided by A, which will equal I plus J. So it does end up being an integer, so we can say that A divides the sum if it divides each of the individual terms. Another thing that we can say is that if A divides B, then for any other integer, A divides B times that other integer, some multiple of B. And then if A divides B and B divides C, then A divides C. So if C, well, let's go ahead and, since I did it for the first one, let's do it for the other ones. Okay. So this means B divided by A is equal to, let's say that it's equal to I again. Then B times C divided by A will equal B over A times C, which will equal I times C. So another integer. And then the third one also shouldn't be too surprising. If B divided by A is equal to I, and C divided by B is equal to K, then this one's going to be a little harder. C divided by A is going to, C divided by A is going to equal C divided by is going to equal BK divided by A, which will equal B over A. Legibly today, but that's normal. B over K, A divided times K, which will equal I times K. Okay. So if A divides B and B divides C, then A is going to divide C, etc. So we have ways of combining these things together and to wind up with results that are somewhat predictable at this point. We've used these. You've probably used them multiple times in your life without even thinking about it. We'll use it in factoring and other stuff like that, which all comes from the idea of the division algorithm. And it's called a division algorithm, but to be honest, it's not really an algorithm. we call it an algorithm, but it's not. Basically, what we have here is, if we say A is an integer, D is a positive integer, then there are two unique integers, a quotient and a remainder. In this case, the remainder is going to be between 0 and D. Remember, D is a positive integer, so our remainder is going to be positive. And then A is always going to equal D times Q plus R. The key thing here, and the gotcha that will happen over and over and over, is that for them to be unique, D has to be positive and R has to be non-negative and less than D. So those are the two things that are going to be an issue. They have to be non-negative with R less than D. And it's a definition of modulo arithmetic. So Q is equal to A div D, and then R is equal to A modulo D. So the quotient here is the quotient that we would expect. The remainder is the remainder that we would expect, at least from a mathematical perspective. There are some differences in the way that this is implemented in hardware. In fact, you'll find this in Java, Python, C, C++. Almost all programming languages are going to do it from the practical perspective versus the definitional perspective here of the algorithm. So they're not going to be mathematically correct. Let's do a quick example here. Up one. Oh, that's the one. I don't have it here. Turn it. Let's do a new program. We'll do yes, I want to change it. Okay, you can take that message. So if we were to write up a program here, a really quick one, this would be, pardon me. Actually, number theory. So math encompasses so much more than just some of the mundane stuff that kids do in school. Include, oops, wrong character. Include, will include, assuming I can type, include IO streams, so I can actually use some input and output. I'll do a using namespace standard, and here I'll do an int, main. I'm not going to provide any command line arguments, so I'll just make this empty here, and inside here, some other curly braces, and so I want an integer n, or pardon me, let's go ahead and name them the same thing. A, comma, B, comma, or D, comma, Q, comma, R. So let's see out. The division algorithm. with the requirement R okay, so what we're going to do is you can always try this stuff out pretty quick. Please enter a value. And Q, the blank line between them. Q is A, integer division. How can I force, oh, they're integers, so I should get this. A divided by D. And this is my green line. Where's my green line? What column am I on? I must have turned it off accidentally. And R is A modulo I can see it on, my one display. I can see it on the other display. We can live with that. Okay. All right. So what we're going to do is we're going to enter some numbers, and we're going to see if this holds. So I will save that. Go over here. We'll bring up a window while I'm doing this. Here. So not too much going on. We'll open a terminal. This is how I normally grade your programs. I go into Bash, which opens my Windows subsystem for Linux, which I've already run today, so it should pop up in about a second. There we go. And I can do G++. I use the new compiler, and here this is modulo P. I might have an error somewhere. D. Oh, that's right. It's D. Typo. Exclamation point, exclamation point. I can do the same command again. Take it out. When you compile, that's the one you get. So the division algorithm states A is equal to D2 plus R, where R and D are non-negative or positive. So A, what do you want A to be? Obviously, we can do it with positive numbers. Let's say A is, we had 43 before. And D is 11. So there should be unique numbers. So what we have are unique values. The quotient is 3, so 3 times 11 is 33. If I add 10 to that, then I'll get 43. There are no other numbers that will fit that equation, and where R and D are both positive. So now let's try negative 43. Oh, pardon me. We'll do the A dot out, and we'll do a negative 43. D, oh, I also prompted for it with it. So D, we want to be 11 again. What would we expect based on what we're looking for here? A is 43, D is 11, and R must be positive. So Q should be, how do I get a positive remainder? How can I get an R that is positive here? I can't do negative 3. That's what we have with a positive value. Because if I do negative 3, I get negative 33. How do I get to negative 43 from that? My remainder would have to be, begins with a neg and ends with a tib. And we can't have that. They both have to be non-negative. So D is 11. If I do the division here, that means that my quotient, negative 43 divided by 11, should be tough room. 4. Or pardon me, negative 4. Because if I put a negative 3 in there, I'm going to get a negative remainder. And I don't have negative remainders with my division algorithm. So, but if I use negative 4, then at that point, R is going to be a positive remainder, and it's going to be, how do I get from negative 44 to negative 43? I add 1. So that's what we expect from math. Our mathematical or our number theory tells us that. Let's see what our programming language does. Blow this up a little bit. Programming language says, it gives us a negative remainder. So try this in Python, it will do exactly the same thing. So while this is the mathematical definition of how division is supposed to be done and defines modulo and everything else in specific terms, when it comes to our programming languages, in general what we're going to do is we're going to divide the magnitude and keep the sign, and then we're going to wind up with a remainder that is the same sign as A as opposed to always being positive. So if D is always positive, then we're all set. But what this allows us to do is we can also do something like, I'll show you the other cute thing you can do on Linux or any bash command prompt. So if you have a Macintosh, you can, or a Mac, you can also do the bash command prompt. Exclamation point dot, the last command that I did that began with the dot was the dot slash a dot out. And if I do exclamation point dot, it will, oh wait, I want to recompile. Then G, that'll recompile. And then a bang dot, and that gives me the program running again. And now if I enter, let's say that I enter a negative 43, and I was going to enter, we do have the possibility of entering negative 43 and negative 10. Negative 10. So we can enter, pardon me, negative 11. We can enter negative values here. And now we get a positive quotient and a negative remainder. So we get, as I said, we get more practical results with our computer programs. They don't necessarily follow our number theory definition of the modulo and the integer division. So 23 mod 6, if I were to do this in with my number theory here, my division algorithm, what should I get? You get a positive remainder. My quotient would be, once again, a -4, not a -3. But what we'll see if you run the same thing on the computer, 23. Bring up my program again. That, and we want -23 and 6. We should get -4 and +1, but what we get is -3 and -5. So, as I said, it's a much more practical thing, and it's the way people probably think of these most of the time. They don't follow this, though this does form the foundation for a lot of the math that we end up doing. 23 modulo -4 shouldn't be defined according to our answer, or pardon me, not our answer, but our division algorithm here. So we can do that as well. Exclamation point. There. And here, if we do a 23 modulo -4, so we get -5 and 3. Pretty much what you would expect. We end up with a smaller value for the quotient as opposed to a larger value. We also have what's called modulo arithmetic. Modulo arithmetic is used. It forms a foundational concept for encryption and for many of the operations that we perform when we're trying to encrypt data, decrypt it, encode it, and decode it. Both work on these. Our definition for modulo arithmetic operations works on the idea of what a modulo happens to be. It's pretty much as you would expect, in that when I write one, I would write something like plus with some modulo value down here. For example, I can do a +8 or a +1024 or a +1023. It's something that tells me that I'm doing modulo arithmetic. But the way they work is really pretty simple. And it's not just plus. I can do a times with a modulo, like modulo 7, or whatever I want to do. I would just write the operator with a subscript to indicate what modulo I'm using. And here's an example. A plus some modulo b is the same as a plus b modulo that value. So it's pretty much what you would expect in terms of the way that it works. The subscript indicates what modulo is going to be applied, and the operators themselves are kind of doing that. The question is, why do we do this? Well, once again, we're kind of skirting the edge of mathematics here and how mathematicians look at things. But we use them for hashing, we use them for encryption, we use them in order to avoid overflow in the arithmetic that we're performing in the computer. All of those are reasons to keep in mind that we have the capability of doing this sort of thing, or to find a useful thing that we operate, way to actually operate on. So how do we represent a number? How do you represent a number in base 10? If you were to describe it to somebody, how would you describe it?
There's like 10 different types of digits, which I know, like you coming from like a base 8 society, that's like 2 more than you think.
Oh, no, base 3. So we have some number. Somebody will throw it away. We have some number of symbols. And this is called okay, and
then once we exceed the number of symbols, we tack on another one in front of the first one.
anything else? So is that something like, I, kind of. This one breaks down when we reach, excuse me, the next number. IB, V, VI, VII. This is not the kind of number system we use today. So we have a couple of different ways to do it. It's surprising that the Romans were able to do anything in terms of engineering or other concepts like that, in part because they had this silly idea that you could represent numbers with only a couple of different letters. They kind of combined some of the ideas. But all of our modern numbering systems are basically position based. When it comes to an integer, we have what we would call our base is normally, you said how many symbols do we have?
3.
Okay. In most of the world today, we use how many symbols? 10. So we use a decimal or a 10-based system. So in general, we have a decimal point, and then the position indicates some power that we have there. For example, here, if B is equal to 10, then this is the decimal. But the general term for it is is the radix. We could call it a binary point in binary, a hexadecimal point, whatever. We could call it based on the base that we're using, and that's what we normally do with a decimal, when we're talking about base 10. But the actual term is radix, and what that indicates is these are all negative powers increasing that's increasingly negative as we go to the right, and these are increasingly positive. And that's going to be true whether we're talking base 10, base 2, base 8, base 16. The most common values that we're going to use in computer science are what? Base 2, because when you look at digital design inside a computer, what you have is a base 2 system. So it's Boolean algebra. It's just that we combine circuitry in order to be able to make it not just values of zeros and ones, but we can combine sequences of zeros and ones to represent binary versus Boolean. Boolean would just be true or false. Binary has an actual value. It's just a representation of the same kinds of things here. What else do we use in computers? One of these is not used very much anymore. Octal. We used to use octal because we were, let's see, when you had computers that were limited to, well, some of the early computers were 8-bit computers. So you basically did 8-bit mathematics, and then you could combine multiple things together in order to do things. So octal was one of the things. So computer bases would be 2, 8, and 16. They're the most common. So, and the reason why we use this is this represents 1 bit, can store 2 values. This represents 3 bits. So, and it's really more legacy than anything else. I have not seen octal used for what. I honestly have not seen octal used for quite some time. If I were hazard to say it, I haven't seen octal used this century. And then 16, this is 4 bits, so 2 digits for a byte of data. So since we usually look at memory in bytes, and since it's byte addressable, that's commonly how we would end up doing it, then using hexadecimal gives us a shorthand way of using 2 symbols to represent the 8 bits rather than 8 ones and zeros, which are easy to get lost in. So using hexadecimal gives us a much easier way of representing larger values. Like if I write a 32-bit value, like that, it gets a little hazardous to try and deal with. But if I write this in hex, then it becomes a little simpler to say, oh, that's what that is. I did 2 9s. So B6, B3, 9E, 1 9 would be the hexadecimal representation of that. And it's a lot easier to say that than it is to say 101. 110, 1011, 010, 11, 0011, 1001. It's a lot easier to get lost. Well, because of the notation that we use, it becomes very easy to represent these as polynomials. And this is actually part of your so any integer can be represented, actually any number can be represented this way. It says that we usually reserve this for integers. We represent it as a polynomial. The value of this is going to be the symbol or the coefficient for a particular position. So, for example, here I've got 0 through 4. So the largest value I would have here would be 4, and this would be the fourth coefficient times the base raised to the fourth power. So, and we do that all the time. It's just we don't normally think of it as, oh, I'm actually using a polynomial to represent, 27,361. So I've got tens of thousands, hundreds, tens, and ones digits. 2 to the 0, 10 to the 0, any number raised to the 0 power is 1. So that's why this ends up being our ones digit, and then the next power digit, the next power digit, the next power digit. All numbering systems that we use inside computers operate this way. About the only variation would be something like big integer in Java. And I don't know what the internal representation of that is, but my guess is that it's still just extending the set or the numbers that we're using by declaring them as a string of bits and then manipulating them that way. I'd have to look at the Java language definition to figure out how, or actually probably just that library. But the result of this is that we can convert from any base to any other base, assuming that you want to do integer or division in from base 11 to base 7, using division in base 7 to 11. So usually what we do is we actually make sure one of these bases is one of them that we're familiar with, base 10, and then the other one is a base that we're trying to get to, or trying to transfer from. So normally we will do this by alternating modulo and integer division, normally using base 10 with base 2 or base 10 with base 16. So let's do a conversion. So 10,327, and this is base 10. Base 10. So if I want to convert this to binary, how would I do that? One thing I could do is I could list my powers. I've got 1s, 2s, 4s, 8s, 16, 32, 64, 128, 256, 512, 1024, 2048, 4006, 8,192, 16,300. So luckily I don't have to go any farther than that. That's about the extent of my, I once had a colleague at the Air Force Academy that made his cadets memorize the powers of 2 up to 20. I don't do that to people because I don't remember them after this. I figure I can multiply by 2. So this is, let's see, this is 10, 11, 12, 13, 14, 14. I don't know So 20 would be 1 million something. So I'd have to multiply by, I could multiply 1024 by 1024 and get the result. But I've never bothered to do that. I don't memorize, I haven't memorized those, but I probably, I might someday do that. Oh, I'm going to have to make those smaller. So I know I'm going to have to go out at least to 13. We'll do 16, 15, or pardon me, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 3, 2, 1, 0. I still ran out of room. Those two are too big. There we go. So now, I've got 10,327. What I'll do is I'll subtract 8,192. And what I get is a 5, and a 3, and a 1, and a 2. So that means 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13. If I get a 1 there, these are zeros. I don't have any of those. So now, will 4,096 fit in there? Can I subtract 4,096 and still have a positive number? The answer is no, so I'll put a 0 there. 2,048 fits, so now I have 2135. I'm trying to leave some room at the bottom to do more. In case you can't tell, and I can't get my computer internet. I keep thinking I'm trying to push. Maybe there's something going on with my 2,108. So that'll give me a 7. A 12 minus 4 is an 8. And I'll have a 0 and a 0. So I'll have 87 left over. So I will have a 2,048, but I will not have a 1,024, a 512, a 256, 128. I will have a 64. So I'll have 87 minus 64. And that's going to equal 23. So I'll have a 64. No 32. 16 does fit in there. So I'll have a 16. And I'll have, that'll be 23 minus 16, which is equal to 7, which means I don't have any 8s. I do have a 4. 7 minus 4 is equal to 3. I do have a 2. 7 minus 2 is equal to 1, and then I have the 1. And so that would be my number. That's a pretty tedious way to do it. That's why I call it the brute force method, is to go through and figure out what power of 2 fits in and how you can press forward with it. The easier way that's your associate's degree exam. The easier way is just to alternate modulo and integer division. So if I have 10, 3, I usually write it this way. I just write the number down. And this will be my quotient and remainder.
Now I'm gonna convert to base 10 here, or from to base 2. So what number should I be dividing by? So I'm going to use the base for these operations. Binary is base 2, so I'm going to be doing modulo 2 and division by 2. So to go from base 10 to base 2, I do modulo 2, and then I'll do division by 2. So my remainder is my modulo. Well, 10,327 modulo 2 is going to be a 1. It's an odd number. So if I have an odd number, I'm going to have a 1. If it's not an odd number, I'm going to have a 0. So I have a 1, and then I end up with 5, 1, 6, 3. So that's my integer division, or divide by 2 here. So this is divide by 2 and modulo 2. Are the two things that I'm using here. So now I have another odd, so I'm going to put a 1 there, and here I'll have a 2, 5, 8, 1. And then I'll have another 1, and then I'll have a 1, 2, 9, 0. Now I have an even, and that gives me a 645. That's an odd. That gives me a 322. That's an even. That gives me a 161. That's an odd. That gives me an 80. That's an even. Divided by 2 is 40. I'm going to continue on the next column, so I have 40 here. I'll just continue on with that. So 40 gives me a 0 and a 20, and a 0 and a 10, and a 0 and a 5. And then I have a 1 and a 2, and a 0 and a 1, and a 1, and a 0. So as soon as I get to 0 here, I'm done. Which one of these is my least significant digit? What does least significant mean? It's my ones digit. It's the first one. Because that's the one that tells me it was an even or odd number to start with. So this is the L, S, B, and this is the LSD, most significant digit. We usually put D or B for bit, but here I'm going to use D for digit. I've only got the digits 1 and 0, but what that means is that my number then becomes 1, 1, 1, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, 1. Which should match 1, 0, 1, 1, 0, 1, 1, 2, 3, 4, 1, 2, 3, 4, and then 1, 0, 1, 0, 1, 0, 1, 0, and then 1, 1, 1. So they're the same numbers. If you can figure out whether a number is even or odd and be able to divide a number by 2, then this becomes a very easy way to do the translation from one to the other. Now I'll show you the true magic, which is going the other direction. Going the other direction, this is what I have. So what I'll do is multiply by 2. And then add So I don't do the multiplication after the last addition that I have there. So one of the ways to do this would just be to say, okay, this is 7 plus 160 plus, let's see, this is 4 times 256, so this is 1,024. What am I doing? 256, 512, and 10, 256. And that would be my 1024 plus 512, 36. And then 3 times whatever the next power of 16 is. So I can go through and either do powers of 16, or I can do each bit and say this is 1 plus 2 plus 4. No, 8, 16, 32, 64, 128, 256. I've got 1024. No, 2048. I've got 4096 and an 8192.
So then I just add all those up, and that would be the way to do it. The other way to do it is to look at the number and say I've got 0, 0, 1, 1, 0, 1, 0, 1, 1. So if I've got more than one digit, I add the digit and multiply by 2. So I start with 0. 0 plus 0 is 0, so I get a 0. Add the next digit, I get a 0. Multiply by 2, add the next digit, I get a 1. Multiply by 2, add the next digit, I get a 3. Multiply by 2, that would be 6, add the next digit, I get a 6. And this might be easier to write it in a different way. So now, multiply by 2, add the next digit, I get a 13. Multiply by 2, add the next digit, I get a 27. Multiply by 2, I get a 54. Multiply by 2, add the next digit, which is a 1, I get a 109. Multiply by 2, add the next digit, I get a 218. Multiply by 2, add the next digit, I get a 437. Multiply by 2, add the next digit, I get an 874. Multiply by 2 and add the next digit, which is a 0. I get a 16. I get a 17. 48. And then I get a 3497. That takes care of that one. And then I get a, let's see, that'd be 6934 or 35, 6935 after I add the 1 bit. Then I multiply by 2 again. I get a, let's see, this is 13. Oh. I get a 13
So that's what I got that way.
This is the easy way?
Maybe not. With big numbers, I mean, you just multiply by 2. This would be what would happen within the computer for trying to determine the representation. Is you multiply, you add, you could add each bit and multiply by 2, and then add the next bit, and do that for all the bits, except for you don't do the multiplication after adding the last bit. We can check our answer here, calculator, and we have our programmer calculator. So what I have here in my programmer calculator, a little bit easier to see. So what I'm going to have is I don't have a number pad, so I'm going to have to go binary input, and I'm going to go type in 1 1 0 1 1 0 1 0 1 0 0 1 1 1. This is the easiest way. Just pull up your calculator. But as you can see, I'm off by a factor of 10. Or actually more than that. 13.9. So I messed up somewhere over here. 13.9. Yeah, it's in one of these two, I think. But you can, if you're very, very deliberate with it, you can just multiply by 2 every time. So I have, let's try it top to bottom. And I'll do this in a different color to show that we're doing a different case. 0 0 0 0 0 1 1 0 1 1 0 0 1 Okay, so I start off at a 0, multiply by 2 and add the next number. 2 times 0 plus 0 is 0. 2 times 0 is 0 plus 1 is 1. 2 times 2 plus 1 is 3. Times 2 plus 0 is 6. Times 2 plus 1 is 13. Times 2 plus 1 is 27. Times 2 plus 0 is 54. Times 2 plus 1 is 109. At least get that far? Okay. Times 2 plus 0 is 218. Times 2 plus 1 is 437. Times 2 plus 0 is 874. Times 2 plus 0 is 17. 17, and then I've got a, let's see, I've got 40. Times 2 plus 1, that's 3496, 3497. Times 2 plus 1 is, that would be 6869. And that would be 90, yeah, just 90, so this is where I messed up. And then times 2 plus 1, well, that's 5 less than 4,000. So, let's see, there'd be a 0 on the end here, so I'm going to be adding a 1. That'd be 190, so I'd have a 9 and a 9, and carry 1, so it'd be 13, 9, and 9. Add 1, and I get 1. Yeah, so I mismultiplied on this one. Math error. But I multiplied by 2 there. I did the math wrong in my head. It happens. But you could write a spreadsheet for this too. Not that you need it, because usually there are tools in there that allow you to do that. So, but those are practical ways to have nothing more than either addition, multiplication, or division and subtraction, the modulo. So modulo and division, or multiplication and addition, in order to do your conversion from binary to decimal. There are some numbers that have no factors or divisors. So, special class, they only divide themselves and 1. Sound like anything you know? We call them prime numbers. These are the ones that are divisible only by themselves and 1. The small ones, 2, 3, 5, 7, 11, 13, 17, 19, 23, on and on that way. Every integer can be made using a set of prime numbers. We call this the prime factorization of a number. If I list all the numbers with the repeats, it's a prime factorization. If I leave out repeated numbers, we would call it the set of prime factors. So it's not the factorization, because the factorization implies if I divide every number listed, I'm going to get the result. With the factors, it means whether I'm ignoring anything repeated. So it'd be the set of numbers that if you multiply them together some number of times, then once or more, then you get the right thing. So the key thing here is that prime factors are not the same as prime factorization. As an example, if I have 36, the prime factors are 2 and 3. The prime factorization is 2, 2, 3, 3. 2 times 2 is 4, times 3 is 12, times 3 is 36. Yes?
What's the prime factorization of 1?
Of 1?
Yep.
There are no prime factors for 1. Prime 1 is not a prime. It doesn't have a prime factorization because it's smaller than the smallest prime. So you can't multiply prime numbers together to get 1. 1 and 0 are special numbers, that's all. So we don't, there is no prime factorization for 1. Because you can't multiply a set of primes by each other to wind up with that as a result. So the question is, how can we check for prime, whether or not a number is prime?
If they are divisible by more than 2 numbers, like the 1 in itself.
If it's divisible by any numbers other than 1 in itself. So if we go to our notation, if A divides P, A divides, I don't say B, then B is not prime. Unless A. The only time any number is prime, if the only number that divides it, if A is equal to B or A. If A is equal to 1 or A is equal to B, that's the only time that it actually. So how can I then check this? Every number is always going to be divisible by 1. So I would start with 2. How far do I have to go? I start 2, does 2, if B modulo 2, or if, if 2 divides B, then B is not prime. But if 2 doesn't divide B, if B modulo A or 2 is zero, or is not 0, then that would mean that it's possibly prime, or not prime, it's possibly prime. Unless B is equal to 2. But how far do we have to go? I can loop through all the numbers less than it, right? If it's divisible by any of them, then I'm going to wind up saying that it's a prime number. Do I have to go to all the numbers up through the number n that I entered? Okay, I hope you guys are winning your games. What is it, Subway? What was the one that everybody used to play? Had the Subway and you collected coins as you were jumping on top of the subway trains. And, yeah. We only have to check up through the square root of n. Why is that? Why don't I have to go up to n? Well, for any number, the largest factor that I can have in it, assuming that it's not a prime number, is going to be the square root. Or it's going to be smaller than the square root. So if there is some number, a factor, something that divides n that is larger than the square root, that always means that it is multiplied by another number less than the square root in order to equal the number. So as an example, let's say that I'm looking at 90, I don't want to get a prime number here. Let's say that I'm looking at 124. Let me do a little quick math here. Let's see. I need my scientific calculator. So let's try 147. If we have 147, we have 147, what are my prime factors? It's not divisible by 2. Is it divisible by 3? So the answer is yes, it has a 3. So if I divide by 3 here, I'm going to get a 49. So I've got 7 and 7. Darn, that's not quite what I wanted here. Let's see. Oh, clear. Where's my square root? Oh, there it is. No, that doesn't cut it. Okay, that'll do. So let's do 51 instead. So for 51, the square root of 51 is going to be greater than 7, right? But if I start factoring it, if I divide by 2, that doesn't work. How about 3?
Yep.
Okay, so 3 is a factor. 51 divided by 3 is equal to 17. 17 is or is not prime. 17 is prime, so I can't factor it any more than that. But as soon as I hit 3, I found out it was not prime, even though the number that was bigger than, I have a number bigger than the square root. It's a factor of it. My square root's about 7, but 17 is a factor of it. But if I've got 17, a number greater than the square root, I've also got 3, a number less than the square root. Because I've got to multiply that times that to get the number n. So if there is any factor less than the square root, then it's going to be, then it's not going to be a prime number. And that's really all we're trying to say. The result is no prime factors from 2 to the square root, then there aren't any prime factors greater than the square root. All you have is the number itself, which must be prime at that point. So I only have to check through the square root. How can I do that? Well, what if I don't want to use the math library? If I never can remember which math library I'm using. By the way, in Visual Studio, it'll pull the math library in for you. I use an actual standard version of the C++ compiler under new CC or new G++. It will not pull the library in for you because it is not a standard part of the language. So you have to have an include statement. But here, all I have to do is for I equal to I less than, pardon me, I times I less than equal to n plus. This is a loop that checks for primeness. In other words, I check 2, which is my first prime number, and up through the square root of n. I times I, if it's equal to, then I is the square root. So that's one way that will actually do it for you without pulling in a special library. It's also cheaper than having a square root function. The square root function requires more computational time than a multiplication. Let's finish up here. Actually, we'll do this at the beginning of next class. I don't have a lot more material on number theory. I was going to try and give you Thursday off. I could probably still do it if you wanted to go for about 5 minutes. But that'll give you enough material for the assignment that's coming up.
So for any, the greatest common divisor, least common multiple, for any integers a and b, a times b is equal to the greatest common divisor times the least common multiple. That is Theorem 5 from the chapter of the textbook. The proof for that is also in the textbook. For the greatest common divisor, Euclid actually came up with an algorithm for this. It's possible that somebody in Babylon came up with it earlier, or the Sumers, or we're just now beginning to discover. I'm trying to remember what it was. It was there was a cuneiform tablet that they just translated within the last like 5 or 6 months. That is a set of sines and cosines expressed as ratios of sides. So it allowed you to do geometry or trigonometry like 1,500 years before the birth of trigonometry, so to speak, in the Greek world. We call it Euclid's algorithm for the greatest common divisor. There are a couple of different ways to do it. We can do it. Most of you have probably seen it as what kind of algorithm? Begins with a re, ends like a writing style. Recursive. Yeah. The recursive algorithm. Recursive is probably the most common way to see it. You can also do it iteratively. If I were a betting man, I'd say that Euclid probably did it iteratively. So as a couple of examples here, I've got an iterative version. On one side, r is equal to the remainder. Actually, this is not even the one I really like. I like the one I like best is actually a subtraction one, where you just subtract the smaller one from the bigger one, and you just keep doing that until 1, 1, 0, or until they're equal. So that's the fun way to do it. I've actually got an algorithm in one of my solution program for this that does it that way. The most common ways on the right here, Euclid's algorithm is a recursive algorithm. In this particular case, it will work in C++. I haven't looked at the language to figure out why, but it does work in C++ even if A is greater than or equal to B. So the modulo evidently is more resilient in C++. But here, you basically, we call it, if B is equal to 0, we return that A is the greatest common divisor. Otherwise, we return B with A modulo B, where A modulo B will always be less than or equal to B. And that's it. So, sorry, I took an extra 4 minutes of your life today. We started a couple minutes late. So, but that'll give you the background for getting started on the next program. It's another one where we're pulling two things together and just saying, okay, find out whether these two numbers are prime, do the greatest common divisor and the least common multiple of them, and then enter something else, or actually that's about it. Greatest common divisor, least common multiple, and then we're done. So that's the number theory that we're doing. It's determining if two numbers are prime, and then determining what their greatest common divisor and least common multiple are. Have a good time. We do not need to meet on Thursday. I will be here if you need help with anything, or you just feel like you got another class and you just feel like coming home. I'll leave you alone if you want to work on something while you're here. But I won't have any lecture material on Thursday because we've covered it all. You need everything you need to know. You know now. So you can go on with the rest of your life and never learn anything.